who will be talking on breaking the rules, one of my favorite topics, breaking the rules, the parity of the psi difference,
Cascade hyperon.
Psi? Chi.
Yeah.
Thank you. Let me say it again. Breaking the rules, the parity of the chi hyperon, right? And Mr. Nicholas's mentor is Dr. John Price from the physics.
Thank you very much. I'm Dylan Nicholas, and I'm going to kind of pick up where my colleague Cornell kind of left off. He was talking about multiplets, and I'm going to go a little bit into that, not too much, but I'm going to talk mainly about parity. And he kind of gave a breakdown of particles that we know, protons and neutrons. They are made of composite particles known as quarks. The neutron is made up of two down quarks and an up quark. The proton is made of two ups and a down. Now, a hyperon, as Cornell mentioned, is in the same multiplet. And a multiplet can be thought of as kind of I don't want to say it is like the periodic table, but it's in terms of how it's organizing particles in terms of similar characteristics, but in a way, in terms of similarities, parities, it is. And a hyperon happens to be in the same multiplet. A hyperon is a baryon that is made up of at least one strange quark with no charm or bottom quarks. Now, I mentioned parity, and so did Cornell. Parity, physically, you're looking at symmetry between physical properties. Mathematically, you're taking components. Basically, if I take x and let it go to negative x, and I look at what happens, that'll tell me something about the parity. If nothing happens, it looks exactly the same, you're going to get what is known as even parity. If I let x go to negative x, and you notice something completely different, it goes to odd parity. Now, the multiplets, as Cornell mentioned, are organized into spin and parity. Now, when we consider the state of a baryon, it's the state of its quarks, its space, and spin together. In a multiplet, the state of these two states are the same within a multiplet, and this is the one that changes. The parity of the proton is defined to be 1, so we can't exactly measure that. It's defined to be 1. That's why we run into trouble. The parity of the neutron, because it has different additive quantum numbers, namely the charge, we can't compare that to the proton, so we will set it equal to that of the proton. So where are we left in terms of looking at parity within the multiplet? We have the cascade hyperon. The cascade hyperon, I'm going to come back to that in a second. I'm going to define the parity operator. The parity operator takes x, and let's go to negative x, and then I'll give you positive or negative. With the proton, if I use my parity operator as defined, it will give me the proton itself, because even parity is defined to be that way. Now, my parity prime, sorry, I'm missing something here. It should be e to the I s pi times psi of x. The problem here between this step and this step, if we look at parities of our lambdas, is that the lambdas are, if I put lambda, if you look at the parity of lambda for pi, for this top parity operator, I'm going to get lambda plus. If I look at the pi prime, I'm going to get lambda minus. But if I look at the parity of the proton, it's going to give me both even parity. So, however, they both should work equally as well. So how do we solve that issue? Well, if we look at the cascade hyperon interacting with a proton, giving us two lambdas, we're looking at the wave function squared. Okay, and the parity of this cascade proton should be equal to that of the parity of the two lambdas, because strong interactions conserve parity. So, if we look at the parity, if the parity of our lambdas or isotropic and unparallelized, then we have an S wave, and the momentum is going to be zero. Anything other than that, it's going to become way more complicated, and I can't really go into that kind of math. But if we look at the gamma interacting with the proton, this is going to produce two kaons, two pions, and two protons. And we know we have cascade because of the two kaons. The pions and the protons are produced from two lambdas. Now we know that there are lambdas that are actually going on in this interaction. By measuring the angular distribution and the polarization of the lambdas, we can get the total momentum of the interaction between the cascade hyperon and the proton. Now, by going through this process, this will actually restrict the types of parity that we can get, and will give us these choices here for even parity of the cascade hyperon, and odd possibilities here. What we want to do is through the CBAF beam that we're using, that Nick was going over, we're going to gather lots of information, lots of events, and determine whether or not we have, if we have any cascade hyperons in these interactions by comparing between these states here. So, in conclusion, I know it might be a little under time. We have the right beam, we have the right detector. All we need now is data, and between everybody working together, between Eddie, Cornell, and Nick, we should come up with something to measure the parity of the cascade. Any questions?
So